Hi everybody, welcome back to week 5 of From Morse Code to 4G. This week we're going to cover the 40 years of 1960 to the beginning of the 21st century. This is part 1 of the lectures, and here we're going to catch on some of the key events that occurred in those 40 years that had significant impact on technology. To get there, we have to jump back to the 1940s to World War II. The Army, the Navy did a lot of work with ballistics research because they were shooting artillery shells. And they had to calculate what they called the artillery firing tables. This was a very intense manual calculation that had to be done when they were truing up these things, determining how artillery shells would perform, so on and so forth. So they were looking around and they found a fellow by the name of John McCulloch, who worked for the University of Pennsylvania's Moore School of Electrical Engineering. He had begun in 1942 to design a better calculating machine based on some work that another guy named John Amstoff had done with vacuum tubes to kind of speed up calculation processes. So in 1943, the military commissioned the new computer to begin, and McCulloch, the chief consultant, and another guy named John Eckert, and a lot of Johns I noticed here in this particular activity, became the chief engineer. It took him about a year to design what was known as ENIAC, the Electrical Numerator, Integrator, and Calculator. And it took him another 18 months after the design to finish up, make it work, and by the time the war was over. However, they realized it had a great deal of potential, so ENIAC 1, because there was a 2, was put to work by the military, did calculations for the design of the hydrogen bomb, weather prediction, cosmic ray studies, thermal ignition, lots of other things that were needing to be done that required a lot of intensive calculation. Now, in a nutshell, this very portable computer contained 17,000 plus vacuum tubes, 70,000 resistors, 10,000 capacitors, 1,500 relays, 6,000 manual switches, and 5 million soldered joints. This small little footprint of 1,800 square feet weighed 30 tons, and it consumed 160 kilowatts of power to run. This is not a laptop. So they went back to the drawing books and they created a second one. In this case, ENIAC 2, 1,000 times faster than any other calculating machine that had been designed to date. And this thing was smoking fast. It could do 5,000 additions, 357 multiplications, or 38 division activities. But it used vacuum tubes instead of switches and relays, which had a tremendous result in increased speed. But the downside is this was really difficult to reprogram. Changes could take the technicians weeks, and it also required long hours of maintenance. However, because of the research, it led to a number of improvements in the vacuum tube. So in 1946, John Eckert and McCulloch started the company called the Eckert-McCauley Computer Corporation. And in 1949, they launched BINAC, or the Binary Automatic Computer, which was the first computer to use magnetic tape to store its data. In 1950, a company by the name of Remington Rand Corporation, many of us know them from their old typewriter days, bought their company and changed the name to UNIVAC, division of Remington Rand. Their research resulted in what was known as the UNIVAC, or the Universal Automatic Computer, which was an important forerunner to many of today's computers. In 1955, they merged with Sperry Corporation and formed a company called Sperry Rand. Eckert himself remained with the company as an executive, and he really stayed with the company long into the future, and when it ultimately merged with Burroughs and became Unisys. Now, some of these names might start sounding familiar. Now, back to ENIAC in 1955 at 11:45 p.m. on October 2nd, the power was finally shut off, and ENIAC was retired. Interesting comment in the patent, quote, "With the advent of everyday use of elaborate calculations, speed has become paramount to such a high degree that there is no machine on the market today capable of satisfying the full demand of modern computational methods." That was a quote in 1947 for the patent that was filed for ENIAC. And you know what? It's still true today. Here we go, some pictures. So this gentleman on the upper left side here, he's pulling out one of these massive drawers of relays to perhaps do some reprogramming. I love this picture on the right. You want to talk about spaghetti, the programming process involving cabling. Huge. You can see the size of this thing. It was massive. The lower left corner, you see a vacuum tube, and then you see a transistor, and then you see in the lower right the integrated circuit. That's where we're going with this and why we're talking about this. The work that was done because of ENIAC and a lot of other military research in the 50s, driving the vacuum tube to become more efficient and smaller in size and less power consumption and heat, ultimately driving us to the transistor, which led us to the integrated circuit. The integrated circuit, or the IC. So exactly what is it? Well, it's really simple definition. It's an advanced electrical circuit made from different electrical components that are connected in a number of ways. All right, that's fine. So we talked about that transistor before, right? So the transistors act like a switch. They can turn electricity on or off, and they can also amplify current. Resistors limit the flow of electricity and allow us to control the amount of current. Capacitors collect the electricity and release it suddenly like a battery. Diodes, which we haven't talked about before, but they can stop electricity under certain conditions and then allow it only if these conditions change. So these four main components, transistors, resistors, capacitors, and diodes, are what make up an integrated circuit. There were so many problems trying to create the integrated circuit, but back in the summer of 1958, a guy named Jack Kilby at Texas Instruments found a solution to the problems. He was a new guy. He had to work on a project over the summer break, and so he was working on trying to make smaller electrical circuits. And he saw an opportunity here, come up with his own solution to this miniaturization problem. Why not make all the chips on the component, or rather make all the components on the chip out of the same monolith of material, or the same block of material of semiconductor? In the past, we had discrete components. They're called a transistor, a resistor, a capacitor, a diode. They were discrete, individual. Why not build them all out of the same building block? So he presented his idea to his bosses, and he was allowed to build a test version of it. In the summer of 1958, the first integrated circuit was ready, and it worked right off the bat. Well, at least that's how they say it is. So the first integrated circuit was all purposes kind of crude and simple. Had some problems, but it was groundbreaking because all the parts were made out of the same block of material. All you had to do was add metal to connect the layers on top of it, metal traces. You removed the need for individual discrete components, which we talked about before. Everything was from the same block of material. No more wires to connect all of these components together and do it manually. And the circuits could be made much smaller. The manufacturing process could be automated. This is huge. This was massive. This was groundbreaking. And recognizing the significance of it in the year 2000, Jack Kilby received the Nobel Prize in Physics. He stayed on at Texas Instruments, and he led the team that invented the handheld calculator. Just wanted to show a picture. On the left is the first ever integrated circuit that we just talked about, that was designed. And it looks really funny, right? It was basically homegrown, homebrewed. And as you look at the screen, you can see in the middle there's some little gold traces of gold wire that connect off of this substrate surface. Very messy, very sloppy looking, but you know what? It worked. On the right is the very first ever commercially produced integrated circuit by the same company. A little bit cleaner in design, and the photography wasn't the best when they were doing it, but what you basically see, those pads around the outside perimeter that have traces of foil that goes to the inside, and it's attaching to different components that are built into the substrate: transistors, resistors, capacitors. Not a lot on this one, but it gives you a sense of things. Now we fast forward a couple of years, and we have a far more sophisticated integrated circuit, and this in itself is not nearly as complex and sophisticated as they are today. This is kind of a cool picture here, but you cannot begin to comprehend the amount of components that are built into this integrated circuit and the gold trace wires that come from it to connect to the outside world, if you will, from inside the integrated circuit's plastic case. Now we're going to take a leap, pardon the pun, and talk about the space program, One Small Step for Man. The space race had a huge impact. I cannot begin to describe. We could do course upon course about the impact of the space age, the space race, on the advancement of electronics, computers, all the technology, including Tang, for those of you who may remember those days. When the Russians launched Sputnik in 1958, the U.S. began this amazing crash program to regain or to achieve superiority in space in a number of peaceful ways. It led to the actual mission to put man on the moon by the end of the 1960s. Along with all of the other technology that had to be created and enhanced and developed for this, communications techniques and technologies were driven hard because when you're dealing with something that's going into space, you have to miniaturize. So weight equals fuel, so less weight, less fuel, and there was a huge equation involved in determining the proper allocation of weight for communications, for life support, for any number of other things. So we were driving the pushing to drive to miniaturize our electronics. Now this tied in beautifully with the integrated circuit because that was a logical conclusion on what we could do and have less weight and more capability. There was also a tremendous amount of classified research done in the 1960s from the space race perspective to stay ahead of the Soviet Union and what we then call Red China when we were developing various platforms for intelligence gathering. All of these activities drove technology in the communications arena and the electronics arena to areas that we probably would have taken another 20 years to reach if we hadn't had the incentives that were caused by the space race and the arms race and all of that were involved in that. I'm only devoting one slide to this particular conversation. As I said, we could go on for weeks just about this, but I wanted to tie in the fact that we went from vacuum tubes and transistors to integrated circuits, and then this huge push in the 1960s for miniaturization and advanced communications techniques, because this positions us to be able to start having portability in our equipment later on. ARPANET, the origins of the internet. So we've talked up till now about the technology involved to provide communications capabilities, whether that's landlines or wired radio or wireless radio types of solutions. The internet was taking advantage of these things to, I guess, bring us to where we are now. So we're going to go back to 1962, a bit of history on the internet. A guy by the name of Lichtlinger from MIT. He had a concept called a galactic network, which was sort of kind of cool. He envisioned this global interconnected set of computers that everyone could access data and programs from any site. So back in 1962, this guy was thinking what we use today. He was the first head of computer research at the computer research program for DARPA, which was a defense agency research organization. And then he convinced his successors there, a guy by the name of Sutherland and Taylor, and another one named Roberts, to the importance of this concept of this galactic network, if you will. 1961, Leonard Kleinrock of MIT published the first paper on what was called packet switching theory. And he wrote the first book on this in 1964. Why is this important? The whole fundamental concept of how the internet operates is, in a sense, at the packet switching level. And we're not going to go too deep into this, but it was back in 1961 that these papers were written. The other key step that came along was making computers talk together. So in 1965, a guy by the name of Thomas Merrill, working with Roberts and Kleinrock, they connected. There was a computer in Massachusetts known as the TX2 computer, and there was another computer in California known as the Q32 computer. I love these names. They connected the two together with a telephone line. They dialed up by hand and created this first wide area computer network across country. Honestly, it was very small, very slow, but the first cross-country computer network where two computers were talking together in a non-classified environment was in 1965. So what they realized from this experiment was they could do a thing called time sharing, where computers could work together, they could run programs, they could send and receive data as needed to from remote machines, but that what we call the phones company, the circuit switched phone company, was totally inadequate for this. It could not handle the volume of data. It could not handle all of the technical demands that required faster connection, if you will. So this validated the work that Kleinrock had done on the idea of packet switching. And again, without going into all sorts of technical details, the difference between a circuit switched network and a packet switched network is dramatic as far as throughput for data. So in 1966, Roberts went to DARPA, the defense agency, and he wanted to go to work on developing this computer network concept and put the plan together for what they called ARPANET. He published the plan in 1967. He was at a conference when he did this, and he presented this paper. At the same time, there was a lot of discussion about packet switching, which we spoke about a little bit earlier. So there's a group called the RAND Group. RAND was a corporation that had what they called think tanks, people who sat around and thought about esoteric things that were important for the future. And one of these think tanks had written a paper on packet switching networks to create secure voice solutions in the military in 1964. Now the cool thing about this, we're talking about the classified military development that was going on at the same time the public development that was going on. They were going down parallel paths very, very rapidly. So they took the word packet that was adopted from the work at this conference, the NPL conference, and then they talked about how packet switching could be used for this network that Roberts was proposing called ARPANET, and they upgraded the data speed from 2.4 kilobits to 50 kilobits, figuring that would be sufficient. 1968, they released a RFQ, a request for quote, was released by DARPA for the development of the key components that would be used in this network, known as IMPs, or Interface Message Processors. We're not going to get too deep into all this. You probably won't ever need to remember that again. The RFQ was won by a group known as BBN, Bolt, Baranek, and Newman, out of Boston, headed by a guy named Frank Hart. The BBN team worked with these Internet Message Processor designs with Bob Kahn. And essentially what we did was they created the architecture of the ARPANET, the network topology, if you will, and also the economics that were designed and optimized by Roberts, and also working with Franks and his team at something called the Network Analysis Corporation, and the team at UCLA with Kleinrock. We spoke about him earlier. Your head's probably spinning and you're listening to all this going, wait a minute, what, where, when? Bottom line is, UCLA was selected to be the first node on the ARPANET. And it all came together in September of 1969 when BBN, Bolt, Baranek, and Newman in Boston installed the first node, or IMP, at UCLA, and the first ever host was connected to the ARPANET, the predecessor of the Internet. A month later, Stanford Research Institution, or SRI, was connected to ARPANET, and the first host-to-host message was sent from Kleinrock's laboratory at UCLA to SRI. Now, this may sound very boring, but it was huge. It was so significant. They were using a new concept called packet switching, and they were talking computer to computer. They added two more nodes then, UC Santa Barbara and the University of Utah, and by the end of 1969 there were 4 host computers connected into the initial ARPANET, and the budding Internet, as we like to call it, was off the ground. More computers were added to ARPANET during the following years, and they began developing the protocols for host-to-host communications and other network software. So in 1970, not too far after this, the Network Working Group, under the guidance of a guy named Crocker, they finished the initial host-to-host protocol for the ARPANET. It was called NCP, or Network Control Protocol. And as they added more sites to the network users could finally begin to develop applications. Now we're to 1972. There was a great successful demonstration of ARPANET at the International Computer Communications Conference. It was the first public demonstration of this. Also in 1972, we had what was known as the initial hot application of the cool thing, hot and cold, right? Electronic mail. Email was introduced in 72, and essentially the guy by the name of Ray Tomlinson at BBN wrote a basic email system which could send and receive soft email between the nodes on the network to have an easy form of communications between the programmers and developers. He then later in that year expanded this email utility program to allow you to read, file, forward, and respond to messages. And this is how email took off to become the hottest application in over a decade. So how do we sum this all up? It's kind of cool. The initial ARPANET grew into the Internet, and based on the idea that there would be multiple independent networks rather of a rather arbitrary design. They began with the ARPANET as testing the concept of packet switching. They upgraded it for packet network communications, ground-based packet radio networks. Hint, hint, we're getting close to some of the stuff that cell phones would be doing. The Internet as we know it now embodies, this, as this says here, the key understanding of the idea of an open network architecture. That has led to some challenges from a security aspect, which is outside the purview of this course. But what's really neat is how this all came about. If you want to read a really, really good book, if you can find it, you can find it on Amazon used. It's called Fire in the Valley, and it talks about how this all came together. So let's talk about MCI, or Microwave Communications Incorporated. Actually began in 1963, was a business plan to build microwave relay stations between Chicago and St. Louis so that the truckers along Route 66 and barges along the Illinois waterway could stay in touch with their home base. It began the process of raising capital and asking permission from the FCC to get the appropriate licenses, and ultimately the FCC approved the request. There was another FCC ruling that happened to occur around the same time in 1968, or a little bit later, in 1968 rather, called the Carter phone decision, and this was huge because it mandated that AT&T allow private two-way radio connections to occur with the telephone company. Prior to that, the AT&T maintained that no one could interconnect, therefore they were maintaining control of the network. With the Carter phone decision, the AT&T was forced by the FCC to allow private companies to interconnect their two-way radio systems. So the Carter phone decision and raising of capital ultimately led to, in 1968, a guy by the name of Bill McGowan, a guy from New York with lots of money. He met with the board and recommended that they create a new company called the Microwave Communications of America. And it was incorporated in 1968, and it was the organization that began to build a nationwide microwave relay system. So following that, MCI began building these relay stations, and in 1969 it bought a company or equity position in a company called Interdata, which was another independent regional carrier that was trying to build microwave systems between New York and Washington. And in 1972, MCI began to sell data transmission services. By backtrack a little bit. In 1971, MCOM, as it was known prior to that, was restructured into the MCI Communications Company, and it absorbed the single regional carriers that they had acquired into a single corporation, and it went public in 1972. In 1975, MCI began to experiment offering switched voice services in direct competition with AT&T. Prior to that, they were basically only known for point-to-point voice and data. So why we talk about MCI? Why didn't we talk about Sprint and some of these other phone companies? Well, they were the ones who sort of began the event that became the tidal wave that ultimately led to the consent decree, which broke up AT&T. There were lots of issues about antitrust between AT&T and the United States government. They finally settled some suits in 1974, or rather began the suits in 74, settled in 82, when AT&T, huge, they agreed to divest themselves of the operating companies that were providing local services, and they would be purely a long-distance company. So in separating these parts of AT&T, the local exchanges, that natural monopoly argument started to fall apart. They kept the other group, long-distance manufacturing, research and development, where competition was appropriate. In return for doing this, the Department of Justice agreed to lift the constraints of another decree, which we didn't even talk about, from 1956. So in 1984, divestiture took place, and the Bell system, which had been around since the turn of the century, was dead. In its place was the new AT&T, and 7 regional Bell companies, we called them RBOCs back then. Actually, there were a lot more than 7, because some of them were made up of a lot of different companies. But here's a list of most of the companies that were part of the AT&T phone company prior to divestiture. And I like the logo progression there that you see going from the beginning of the old Bell with long-distance services to the new AT&T. You scan down the list, you'll probably recognize some of your old phone companies there. So that kind of wraps things up for this part 1 of this week's lecture, and we'll see you shortly in part 2.